Hey everyone, and welcome. Today we're doing something a little bit different. We're taking a standard, totally unassuming page from an 8th grade math textbook, and we're treating it exactly like what it truly is, a crime scene of mathematical mysteries just waiting to be cracked. Seriously, if you think geometry is just about memorizing dry formulas, well, prepare to have your mind changed. In this explainer, we're going to sift through the clues, trace the logic, and uncover the hidden rules that literally govern the shapes around us. So put on your detective hats because this is going to be an incredibly fun puzzle-solving journey.
So, here's the challenge I'm throwing your way today. Can you solve these geometry mysteries using just a handful of really basic clues? I want you acting as the lead investigator here. We aren't just going to read off the answers, we are going to actively deduce them together. Every single line, every little angle, every tiny tick mark on the page is a deliberate clue placed there to guide us straight to the truth.
All right, let's dive right in. Here is our primary source material, our official case file for today. This is a page straight out of the Ganita Prakash Grade 8 textbook. Now, at first glance, it probably just looks like a boring list of homework questions, right? Some rectangles with lines chopped through them, a bit of text about circles, maybe a fun little margin scribble. But trust me, this single page is incredibly dense with logical deductions. We're going to use these exact visual clues and constraints to crack today's cases. We'll just start right at the top and work our way down, deciphering the code step by step.
Section 1. The Hidden Angle Puzzles. Finding Missing Pieces. Okay, our very first case focuses on the shapes labeled figure I and figure II. In that first rectangle, we are given a single 30-degree angle tucked down in the bottom left corner, right between the outer edge and a diagonal line. Then, in the second rectangle, we get a 110-degree angle sitting dead center where the two diagonals cross. The question basically asks us to find all the other angles inside those rectangles. To do that, we really have to think about how these intersecting lines, these diagonals, actually interact with the outer frame. Like, what rules are they following here?
See those little tick marks? Yeah, those are massive clues. Step 1, we identify our diagonals. Step 2, those tick marks tell us they bisect each other perfectly, leaving segments of the exact same length. And step 3, well, equal segments mean isosceles triangles. Once you realize that a 30-degree angle on one side absolutely dictates a matching angle on the other, the whole rectangle just unravels like a solved Rubik's Cube. Finding just one single angle structurally locks in all the rest. It's brilliant.
Section 2. Designing with Diagonals. Building Shapes.
Now we're moving from finding missing pieces to actually building the shapes from scratch. Question 2 in our case file poses this really fascinating thought experiment. We are asked to imagine a quadrilateral where the diagonals have equal lengths of 8 centimeters and they bisect each other. But here is the crazy twist. We have to change the angle at which they intersect to 30 degrees, 40 degrees, 90 degrees, and 140 degrees. I want to challenge you to visualize this with me. Imagine two rigid 8-centimeter sticks pinned together right at their exact centers. As you scissor them open and close, changing that intersection angle, the invisible boundary connecting their endpoints completely alters the shape of the resulting quadrilateral. So even though the diagonals remain exactly the same length, that intersection angle dictates the entire soul of the shape.
And that brilliantly sets up question 3. We're told to consider a circle with center O and two perpendicular diameters, PL and AM. Then it asks, what figure does APML make? Well, let's connect the dots from what we just talked about. Diameters of a single circle are always equal in length, right? And they cross exactly at the center, so they bisect each other. Plus, the prompt explicitly says they are perpendicular, meaning they cross at a crisp 90-degree angle. So we have equal diagonals bisecting at 90 degrees. If you mentally draw lines connecting the ends of those diameters, what do you get? Bam! A perfect square. The textbook invites us to reason and/or experiment to figure this out, which just goes to show how deeply interconnected circles, angles, and quadrilaterals truly are.
Section 3. Real-world geometry hacks. Practical applications.
Okay, let's shift gears from theoretical textbook puzzles to something totally hands-on. Here is your mission, should you choose to accept it. You need to make an exact 90-degree angle. The catch? You're out in the wild. We've all seen how to get a 90-degree angle using paper folding, but you have no paper. Zero. All you have are two sticks of equal length and a single piece of thread. How do you do it? I know, it sounds like some kind of survivalist riddle, but it is pure geometry. Take a second to think about what we literally just learned about diagonals.
Aha! The solution is actually hiding right there in plain sight on our source document. If you recall those red handwritten notes scribbled in the margin of the case file, some brilliant previous student already cracked the code.
The note simply says, midpoint, sticks, connect corners, thread. That is the exact mathematical solution translated to physical real-world objects. If you cross two equal sticks exactly at their midpoints, essentially creating bisecting diagonals of equal length, and then wrap your thread around the four endpoints, you physically force the thread to form a rectangle. And, by definition, the corners of that string rectangle will be perfect 90-degree angles. It's just this beautiful moment where abstract mathematical rules apply flawlessly to literal sticks and string.
Section 4. Defining the rectangle. Properties of shapes.
With that real-world success under our belts, let's tackle question 5. This one's fun because it tests a core assumption about the very shapes we've been building. The text poses a tricky question. Can parallel opposite sides be chosen as a definition of a rectangle? Well, let's think about that comparison. A rectangle definitely has opposite sides that are parallel and equal, sure. But imagine a generic parallelogram, like picture a rectangle that someone accidentally sat on, pushing it totally out of shape. The opposite sides are technically still parallel and equal length, but those crisp 90-degree corners? Gone. You absolutely need the full set of constraints to lock the shape in place.
Section 5. The Quadrilateral Angle Rule. Universal Truths.
This brings us perfectly to the final section of our page, Section 4.2. We are zooming way out from the specific definition of a rectangle into a massive universal truth about all quadrilaterals. The text asks us this gem. Is it possible to construct a quadrilateral with 3 angles equal to 90 degrees and the 4th angle not equal to 90 degrees? Just try to imagine drawing this. You draw a straight line, turn exactly 90 degrees, draw another, turn exactly 90 degrees, draw a third. If you then try to connect that last point back to your start point, it is mathematically, physically, geometrically impossible for that final intersection to be anything other than 90 degrees. The textbook gently points out that we might have already observed through our constructions that this isn't possible. But then it asks the single most important question in all of mathematics. But why not?
To answer that big why not, the textbook anchors us to a foundational golden rule. It literally states, we have seen that the sum of the angles of a triangle is 180 degrees. This right here is the crucial stepping stone. Every single triangle in existence, no matter how stretched out, squished, or skewed it is, has interior angles that add up perfectly to 180 degrees. This isn't just a suggestion, it's an unbreakable law of our two-dimensional universe. And the authors of this text are using this established law to point us toward a huge realization.
Which leaves us with the ultimate cliffhanger at the bottom of our case file. The text wraps up by stating, there is a similar regularity in the sum of the angles of a quadrilateral. And that's it. It doesn't give us the answer. It leaves the mystery entirely up to us to solve. Think about it. If a 3-sided shape always has 180 degrees, what happens when you add a 4th side? Can you use that 180-degree rule of a triangle to figure out the universal rule for a quadrilateral? Here's a hint. Think about how many triangles perfectly fit inside a 4-sided shape. I'm going to leave you with that provocative thought. Take all the clues you've gathered today and see if you can crack this final overarching geometric mystery entirely on your own. Thanks so much for joining me on this Explainer Detectives. Keep questioning the shapes around you.